Find the best city to live in. In this problem, a choice must be made between Boston, Los Angeles, St. Louis, and Houston regarding which city is best to live in when moving from Philadelphia. The 5 criteria and their desirable values include a short moving distance to the city from Philadelphia, the lowest cost of living, the most comfortable climate, the highest quality of education, and the highest quality of life. Needless to say, the assumptions, weights, and relative priorities in this problem are subjective and only used as an example to demonstrate the analytical hierarchy process. AHP is a decision support system which ranks alternatives against each other rather than against a standard measure. The ranking of each alternative, S, in AHP is the sum product of the weight of each criterion times that alternative's relative priority for each criterion, where the alternative with the highest ranking is the preferred alternative. It is customary for the weights and relative priorities for each criterion to be normalized to 1. If we create a table which compares the 4 cities based on the 5 criteria using the weights and relative priorities, the rank for Boston would equal the product of the weights and relative priorities for Boston for each criterion. The ranking for LA would equal the product of the weights and the relative priorities for LA for each criterion, and so on. For notational convenience, subscripts A, B, C, and D will refer to the cities Boston, LA, St. Louis, and Houston, respectively. To begin, we'll first calculate the weights for each priority, WI, and then return to solve the relative priorities for each criterion. The weights for each criterion are calculated by comparing each criterion with each other, using ratio scale judgments, and later determining the weights for each criterion. Let's begin by comparing the distance to the city from Philadelphia criterion with the other criteria. The analytical hierarchy process uses scale judgments from 1 to 9, indicating how much more important the criterion in the row is to the decision maker than the criterion in the column. If the distance is slightly more important than the cost of living, 3 is entered into the common cell. If distance is strongly more important than quality education, then a 5 is entered into the common cell. All criteria compared with itself is equally important and gets the number 1. The numbers 2, 4, 6, and 8 are also used as intermediate strengths of importance between the odd numbers. Instead of using 3 and 5 as before, we'll change the previous values to 2 and 2, indicating that the distance is barely more important than the cost of living or education. If comfortable climate and quality of life are more important than the distance from Philadelphia, then a positive integer will be inputted in the comfortable climate and quality of life rows for the distance from Philadelphia column. The remaining values, which indicate greater importance, are entered into the cells. Next, the table is completed such that the value in cell ij is the reciprocal of the value in cell ji. Next, the weights are calculated. Also, a coefficient of inconsistency, Ci, is also calculated. to ensure the ratio scale judgments are sufficiently consistent. If we normalize the values in each column to 1, we notice not even 2 of the 5 columns are equal, let alone all 5. Therefore, we'll calculate the weights as the principal right eigenvector of matrix A. Matrix A contains the Soddy importance factors. W is the weight vector or eigenvector of matrix A, and lambda max is the maximum eigenvalue of matrix A. The weight vector is equal to the limit of AKE divided by E transpose AKE as K approaches infinity, where E equals the unit vector, A1 equals A, and AK plus 1 equals AKA. Successive approximations of the weight vector, W, are made until its values converge within a reasonable tolerance, say, to the nearest thousand. For this matrix A, it took 5 iterations for the weight vector to converge. The variable K also serves as an iteration counter. Before the weights can be used to calculate the rank of each alternative, we should confirm the coefficient of inconsistency is less than 0.10. The coefficient of inconsistency, Ci, equals the consistency ratio, Cr, divided by the random inconsistency index, Ri. The consistency ratio equals the maximum eigenvalue of the 5 criteria minus n, divided by n minus 1, where n by n is the size of matrix A. So in this case, n equals 5. And the maximum eigenvalue equals the sum product of any row I in matrix A multiplied by the weights, divided by the weight of that row, I. Arbitrarily setting I to equal 1, the maximum eigenvalue for the matrix A equals 5.15. If the maximum eigenvalue equaled n, which for this matrix would be 5, then matrix A would be perfectly consistent. The random inconsistency index, Ri, is based on the size of matrix A and equals the average consistency ratio for randomly generated reciprocal matrices of various sizes. Since n equals 5, the random inconsistency index equals 1.12. This makes the coefficient of inconsistency 0.034. Since 0.034 is indeed less than 0.10, our matrix A is sufficiently consistent, and the weights we calculated for each criterion can be added to the alternative comparison table in place of W1 through W5. We notice the criterion for the quality of life has been weighted the highest, and the criterion for education has been weighted the lowest. Now it's time to calculate the relative priorities for each criterion. Taking a closer look at our 5 criteria, we'll solve the relative priorities for the education criterion and quality of life criterion using Soddy's ratio scale judgment comparisons 1 through 9, as we used for the weights. For the distance from Philadelphia, cost of living, and comfortable climate criteria, a numerical process of judgment will be used to compute the relative priorities. Let's begin with the distance criterion and then work our way down through each criterion in order. The number of miles from Philadelphia to each city is looked up and entered into a table. Since the shorter distances are preferred, the inverse of these distances is calculated. Lastly, since the sum of the relative priorities for each criterion should sum to 1, the inverse distances are scaled appropriately. These relative priorities are then entered into the alternative comparison table for the distance criterion. Next, the cost of living criterion is analyzed, and the cost of living in each city for 1 week is added to a table. Since there is less variance in the cost of living than there was in the distance, the percentage of the minimum cost of living is calculated in the third column. The lower the cost of living, the better. Therefore, the inverse of that percentage above the minimum is calculated. Lastly, as with the distance criterion, the relative priorities for the cost of living should sum to 1 and are normalized as such, and the alternative comparison table is updated. The climate criterion also uses a numerical approach for determining its relative priorities, based on recorded temperatures in each city. Next, we'll compute the relative priorities for the education and quality of life criteria. First, we'll subdivide the education criterion into grammar schools and colleges, and the quality of life criterion will be divided into traffic and the arts. Between each subcriterion, relative priorities are assigned, where the relative priorities of grammar schools represent 40% of the education criterion, and colleges represent 60%. Quality of life is broken down to 30% traffic and 70% the arts. The composite relative priorities for education will be 40% of the weight vector for grammar schools and 60% of the weight vector for colleges, and the weighted averages will be used in the alternatives comparison table. Similarly, the relative priorities for the quality of life criterion will be a weighted average between 30% traffic and 70% the arts. Let's begin with calculating the weight vector for grammar schools. Comparing the cities to each other with respect to grammar school education, the ratio scale judgments 1 through 9 are used, as before, where 1 represents equality and 9 represents extreme difference. When comparing alternatives, it would be more appropriate to change the word important to preferred. So if we look at Boston, for example, we might say the grammar schools in Boston are more strongly preferred over the grammar schools in Los Angeles. The grammar schools in Boston may also be preferred over grammar schools in St. Louis and Houston, to varying degrees. Each city compared with itself is equal, and a value of 1 is entered. The remaining preferences are filled in, and the reciprocals are calculated. Next, we'll determine the relative priorities for grammar schools. Instead of calling W the weight vector, we'll call it the relative priority vector. This vector, W, can be solved using the same method as we used to find the weights for each criterion. The relative priorities for grammar school are 0.4997, 0.0912, 0.2906, and 0.1185 for Boston, Los Angeles, St. Louis, and Houston, respectively. Since the coefficient of inconsistency equals 0.009, the matrix A is sufficiently consistent, and the relative priorities are entered into the table. Next, the relative priorities for the college subcriterion are computed. The preferences of the decision maker with respect to which cities have the best colleges are shown here. The relative priorities calculate out to be highest for Boston and lowest for Houston. The coefficient of inconsistency is again acceptably low. The relative priorities for colleges are entered into the table, and the relative priorities for education are computed. These relative priorities are then entered into the alternative comparison table for the education criterion. The last criterion is the quality of life, which is based on 30% of traffic subcriterion and 70% of the arts subcriterion. These relative priorities are solved the same way as were the relative priorities for the education criterion. The traffic comparison tables are shown here, where St. Louis and Houston have lighter traffic than Boston and Los Angeles, and hence have a higher preference for this subcriterion. The arts preferences are shown here, and dominated by Los Angeles, with Boston, St. Louis, and Houston preferred second, third, and fourth. The relative priorities for traffic and the arts are used to compute the relative priorities for the quality of life criterion. Returning to the alternative comparison table, the relative priorities for quality of life are entered. Now we're ready to begin calculating the final rankings. The rank for Boston equals the sum product of the weights and relative priorities for Boston for each criterion, which equals 0.339. The ranks are also calculated for Los Angeles, St. Louis, and Houston, based on the weights, relative priorities, and all other assumptions used in this problem. The best city to live in when moving from Philadelphia is Boston, and the answer is A.